Welcome to This Explainer. Today we're diving right in to demystify a kind of secret language, one that bridges the gap between our human need for readability and the raw electrical pulses of machines. Let's break down exactly how hexadecimal simplifies computer binary.
So picture this. You're setting up a network, maybe trying to troubleshoot your Wi-Fi router, and you're staring at the network settings. You expect to see a normal string of numbers, right? But suddenly, there's a B or an F just kind of staring back at you. It really makes you wonder, why on earth does your Wi-Fi address have letters in it?
You'll often see this cryptic string of characters called a MAC address, which stands for Media Access Control. It's essentially a 48-bit code that uniquely identifies your specific device on a network, so all that data knows exactly where to go. But to figure out why it's written in this bizarre mix of numbers and letters, instead of just a standard string of ones and zeros, we've got to take a quick step back into the very heart of the computer. And that starts with one fundamental truth about computing. Underneath all the slick software we use every day, machines operate entirely in binary. It's a base 2 number system that relies on only 2 states, 0 for off and 1 for on. Now, this perfectly matches the billions of microscopic transistors inside a CPU that are constantly, literally, flipping on and off to process data. And hey, while binary is incredibly efficient for electronic circuits, it is absolutely brutal for humans. It's frustrating, highly error-prone, and ridiculously long for our eyes to read or write out. So we clearly needed a shorthand, right? Software engineers and network technicians just needed a way to interact with these massive binary strings without getting a massive headache. And that brings us to the magic number 16. Specifically, the base 16 number system, which you probably know better as hexadecimal, or just hex for short. Now, how does base 16 actually work in the real world? Well, we're all super used to the decimal system, right? Base 10, using digits 0 through 9. Hexadecimal essentially just extends our everyday counting system. To get 16 unique single characters, it uses those standard numbers, 0 through 9, and then it cleverly borrows the first 6 letters of the alphabet, A, B, C, D, E, and F, to represent the values 10 through 15. So A is exactly 10, B is 11, all the way down to F, which hits 15. This setup brilliantly illustrates the sheer, unbelievable space-saving power of hexadecimal. Just picture trying to read a messy 8-bit binary sequence like 10111000. It's tough to read at a glance, and it's way too easy to mistype. But its exact hexadecimal equivalent is simply B8. We've literally collapsed 8 confusing digits into just 2 clean, distinct characters. It's a total game changer for human communication. So let's look at how this builds mathematically, step by step. The absolute magic of hex is that one single hexadecimal digit equals exactly a 4-bit binary sequence. Computer scientists actually lovingly call this a nibble. So step 1, you take that 8-bit binary number, 10111000. Step 2, you simply split it right down the middle into 2 4-bit sequences, 1011 and 1000. Finally, step 3, convert each chunk into a single hex digit. 1011 becomes B, and 1000 becomes 8. Because of this direct 4-bit relationship, we can cleanly snap endlessly long computer codes into really small, manageable chunks. But I do want to pause for a second here to clear up a very common misconception. Computers do not actually use hexadecimal natively. It still has to be translated back into binary for the computer to use. It's vital to remember that underneath it all, the machine's hardware still only speaks binary. The CPU has absolutely no idea what an F or a B is. Hexadecimal is just the elegant interpreter. It's this presentation layer we use purely to make the machine's raw digital language readable for us humans. And you actually see this translation at work all the time on the internet. Web designers and graphic artists use hexadecimal codes every single day to pinpoint millions of specific colors for websites and digital art. If you've ever looked at HTML or CSS coding, colors are defined using a 6-character hex format, completely bypassing the need to type out incredibly long, tedious strings of binary. Here's exactly how that color coding plays out in practice. The format is basically organized into pairs of hex digits for red, green, and blue. So let's say you want your computer monitor to display a really bright, vibrant yellow. You'd use the hex code FFFF00. That first FF cranks up the red to the absolute maximum. The next FF gives you maximum green, and the 00 gives you 0 blue. This incredibly short 6-character code instantly translates a massive 24-bit underlying binary sequence telling your screen exactly what color to shine.
But hey, it's way more than just pretty colors. This clever shorthand is quite literally the backbone of modern computing infrastructure. Every day, hexadecimal is everywhere. Programmers rely on it to pinpoint precise memory location errors when a computer suddenly crashes. It's used for those 48-bit MAC addresses routing local network traffic that we talked about earlier. And perhaps most crucially for our future, it is the foundation for 128-bit IPv6 internet addresses.
Let's actually look at that internet expansion a bit closer, because it's fascinating. As smart devices completely exploded in popularity, I mean, we're talking phones, fridges, smart speakers, watches, we came dangerously close to running out of the old decimal-based IPv4 internet addresses. IPv4 used a 32-bit system, which capped us at about 4.3 billion addresses globally. And honestly, that just wasn't going to cut it anymore. We were forced to upgrade to the new IPv6 standard. IPv6 uses a massive 128-bit addressing system formatted as 8 groups of 4 hexadecimal digits. Because of the insane mathematical combinations that hex allows, IPv6 gives us a staggering 340 trillion unique addresses. It basically guarantees that every single smart device on the planet can connect without us ever running out of room.
So, we've taken quite a journey today, right? Going from the raw on and off transistor switches of a CPU all the way up to the vibrant colors on your monitor and the incredibly complex routing of the entire global internet. And it is all thanks to the simple, space-saving power of base 16. Now that you know exactly how this translation works, I've got one final question for you to take away. Where will you spot hexadecimal in the wild next? Because the next time you encounter a cryptic string of numbers and letters on a Wi-Fi router, a software error pop-up, or a web design panel, you'll know exactly what secret language you are looking at. Thanks so much for joining me on this explainer, and keep exploring the hidden code of our world.